Hey there everyone, we have an example about transformers. In this example here we have a power station, maybe a dam or something like this, and water flows down. As it flows down, turns around a turbine within the vicinity of a magnetic field, produces a lot of electric energy. This electric energy goes to a substation just outside the dam, and the amount of power that we are getting out of it is 1.1 times 10 to the power 6 watts. Now this power has to be transferred through two wires, 9 kilometers each, to a nearby city, and once it gets there it goes into another substation, but that's another issue. Each wire has a resistance per length that is equal to 5 times 10 to minus 2 ohms per kilometer. Okay, find the power used to heat the wires if the power is transmitted at 1000 volts. So we do have the power first, and we have the voltage. From that we can find the current at which the value of the signal is transformed. Then we can find the power that is going through or being used as heat in the wires. Okay, so first of all, let's use this equation, which is the same. P is equal to I times the voltage. All right, and P is given as 1.1 times 10 to the power 6 watts is equal to I times the voltage at which it is transformed, and that gives us I is equal to this divided by 1000, and we get I is equal to 1.1 times 10 to the power 3 amps. Alright, now to find the power used, we need to find the power. P again is equal to I times E. Okay, knowing that E is equal to I times R. Now we have I from here, we just need R, so put this here, so you get I squared R. So that's the power that we're going to use for this part. And we have P is equal to I squared. Now what is R? We have R per length 5 times 10 to the power minus 2 ohms per kilometer, and the length is 9 kilometers, so multiply 9 by this to get R. Okay, since you have two wires, you have to multiply by 2. So 2 times the length times the resistor per length times 10 to minus 2. Okay, alright, and now if you plug in the values, I square is equal to 1.1 times 10 to the power 3, and that should be squared, times this value, which ends up to be 0.9. And if you do this calculation, you will get the answer to be 1.09 times 10 to the power 6 watts. And that's it for part number 1. For part number 2, we have, now as you can see, this is a lot of loss of power because the current is huge. You would not want to transfer this current, a huge current, okay, for 9 kilometers. That would be a waste. So what you do is just like you step up the voltage more, and that's what's happening here. You're stepping up the voltage by 140 times compared to this one. So the new voltage, which I will call E now, is equal to 1000 times 140, because that's what the ratio is. So this gives us the new voltage equal to 1.4 times 10 to the power 5 volts. So we have a huge amount of voltage coming out now. Okay, well that's good, because according to the power is equal I times E, then power is supplied by the station is the same as the one before, which is 1 times 1.1 times 10 to the power 6. So 1.1 times 10 to the power 6 is equal to I times E. Plug in E here as 1.4 times 10 to the power 5. The only unknown is I. Calculate that and you will get I equals to 7.887 amps. And that's a much smaller current than the one we calculated here. This one is almost bigger than 1100. This is much smaller. Okay, so now we can use this current into this equation again. So we know that the power that we need to find is equal to I squared R. I is equal I squared 8.87 square, and the resistor is the same as this one, which was calculated 0.9. And doing this calculation, we get 55 watts only. That's it. That's what we're gonna lose to heat, if you will. We don't lose energy, we just transform it to useful or unuseful form. In this case, the heat is unuseful form. So from losing almost 1,000,000 watt, we're losing only 55 watt. And that's it for this one. Thank you.